Hello, my name is Praveen Tirupattur. I am a PhD student from CRCV lab at University of Central Florida. I will be presenting our work modeling multi-label action dependencies for temporal action localization. This work was done in collaboration with my fellow student Kevin Duarte and faculty Dr. Yogesh Rawat and Professor Mubarak Shah. Temporal action localization is a video understanding problem where the inputs are long untrimmed videos and the task is to localize temporally the start and end of each action in the video. Here is an example video. This is a real-world untrimmed video which contains multiple actions at different temporal intervals. These actions have an inherent relationship between them. The motivation of our work is to leverage these relationships to improve temporal localization of actions. We in this work specifically modeled two types of relationships. First, co-occurrence, where two activities overlap or occur together. Second, temporal ordering, where one action would follow or precede another. For example, pole vault action always involves running and they temporally co-occur. Furthermore, temporal ordering is evident in this video, where the action basketball dribble always precedes the action basketball dunk. To solve the problem of temporal action localization, by leveraging the relationship between actions, we propose the following architecture. This consists of three main components. First, a long video is divided into individual clips, which are passed through a pre-trained backbone to extract features. These features are then passed through a fully connected layer to learn class-specific features. Once the features are extracted, they are refined using our proposed MLAD layer. Our proposed MLAD layer consists of two branches, co-occurrence dependency branch and temporal dependency branch. Co-occurrence dependency branch learns the relationship between classes in each time step. Temporal dependency branch learns the relationship between time steps for each class. Output of this layer is a weighted sum of features from both the branches. Here, the weight alpha is a learned parameter. In our network, we use multiple MLAD layers in series to model complex action dependencies. The final features are passed through fully connected layers to produce class predictions for each time step. An additional classification is performed on the initial class-specific features to help learn better representations. The network is trained end-to-end using binary cross-entropy loss for multi-label classification. There are several existing multi-label classification metrics as shown here, but they treat each class independently. Since our work focuses on learning action dependencies, we present a metric to evaluate how well a model learns these relationships. Consider traditional precision and recall metrics for an action C. To evaluate co-occurrence dependencies, we propose action conditional precision and recall metrics which evaluate performance on action Ci given that action Cj is present within the time step. To evaluate temporal dependencies, we can modify these metrics to evaluate performance on action Ci given that action Cj is present within a temporal window tau. For more details about our metric, please refer to the paper. Here are the results of our approach on multi-Thomas using our proposed action conditional metrics in comparison with the baselines and the existing state-of-the-art. We also show the comparison with state-of-the-art using commonly used evaluation metric FMAP. Here we show results of various ablation experiments we perform to evaluate individual components of our model. One ablation to note is our analysis on the effect of co-occurrence and temporal dependency branches in the MLAD layer. Using temporal dependency branch alone gives us better results than co-occurrence branch, but we achieve best results with the combination of both. We also analyze the learned attention from both the branches of the MLAD layer. Here, we show the attention from the co-occurrence branch where the attention is between classes within a time step. This visualization shows that related classes have higher attention. Next, we visualize the attention from the temporal branch. Here, the attention is across time steps for a specific class. This checkerboard pattern shows that time steps where the action is present tend to focus on other time steps where it is present. Please refer to the full paper for a detailed explanation of these attention maps. Here, we show the qualitative results from our model in comparison with the current state of the art for a sample video from multi-Thomas. Our predictions are closer to the ground truth in comparison with the current state of the art. Thank you, and please refer to the link below for the training code.
Hello, this is Aisha Uruj Khan presenting our work titled Found a Reason for Me Weekly Supervised Grounded Visual Question Answering Using Capsules. This work is co-authored with Hilde Kune, Kevin Duarte, Chuang Gan, Niels de Vitoria Lobo, and Mubarak Shah. For a given image and question pair, our task is to answer the question and localize the answer objects with VQA supervision alone. Existing VQA systems show high VQA accuracy but poor answer grounding. To solve grounded VQA tasks without using object annotations, we propose to use capsules. Here is our approach. Given a question image pair, we first obtain special features X for the image using a CNN encoder. Question is encoded into sentence feature and word level features when passed through an RNN. These question encodings are input to a multi-hop textual query generator which generates T queries called reasoning operations. We first transform image features into primary capsules, then use EM routing to transform them into visual capsules. Both visual capsules and T-textual queries are then fed into the reasoning process. We introduce a novel soft masking approach which uses weak supervision of VQA tasks and learn to select visual capsules based on the Tth query. More specifically, we use a linear layer over Qt to generate a soft mask for capsule selection. The soft fades are applied to visual capsules to obtain masked capsules. These masked capsules, along with the query Qt, are input to the reasoning modules. Aggregated output of the reasoning process then goes into the output module, which is a classifier to predict the correct answer. The system also outputs attention maps over input image, which can be post-processed to get detected objects. We integrated the proposed capsule module into two VQA systems, MAC and STACKed NMN. MAC is a recurrent reasoning system composed of a reasoning module called MACCell. The control module inside MACCell takes sentence and word features along with the previous output Qt-1 to generate query at time step t. Read module is used to read image information based on this query. We use the same query embedding to do soft masking on visual capsules. These masked capsules are then input to the read module along with the query for rest of the reasoning process. Masking layer is shared across all T steps. Stacked NMN uses the same controller module like MAC to generate T queries. Unlike MAC, Stacked NMN has specialized reasoning modules. These reasoning modules use convolutional and/or linear layers as building blocks to perform reasoning operations. Each of these reasoning modules have a separate soft masking layer and use query to generate a separate mask for visual capsules. Masked capsules, along with the query, are then input to the respective reasoning operations. Training protocol for our approach is same as the baseline method. We conduct experiments on two widely used datasets GQA and Clever. GQA is a real-world visual reasoning dataset with multi-hop reasoning questions. GQA provides grounding labels for objects referenced in both the question and the answer. Clever, on the other hand, provides a visual reasoning VQA dataset with synthetic images. For visual grounding on this dataset, we use the question generating framework provided by Johnson et al. To generate new question-answer pairs with the bounding box labels for the answers. We generate 850,000 question-answer pairs for training and validation set with more than 1 million bounding boxes. Here are the qualitative results on the GQA dataset. For the image question pair, attention over question words from MAC are shown in the orange heat map. Bottom 4 rows below the image are the attention maps from 4 reasoning steps inside the MAC system. And here are the visualizations from MAC with capsules. We can see that while the baseline system tends to attend corners of the image in the intermediate reasoning steps, MAC caps start looking on different regions and quickly locate the relevant object, with better overlap with the ground truth object. Attention on question words for MAC caps is also more relevant. This is another case where MAC caps correctly answers the question with correct grounding of the object floor. Here we compare our system with MAC on GQA dataset. Although MAC performs better than MAC caps in terms of VQA accuracy, MAC capsules is stronger for grounding tasks. When compared on the Clever Answers dataset, integrating the proposed capsule module into baseline systems has a stronger or comparable performance on VQA accuracy. For grounding, our system produces significantly better results than the baselines on all metrics. To summarize, we propose to use capsules for weak grounding of VQA systems. The proposed query-focused soft mask module is generic and shown to be successfully integrated into two VQA systems as an intermediate layer, with significantly improved grounding on GQA and Clever answer datasets. For more details, please visit our poster in poster session 6. Thanks.
Hi, my name is Aliweza, and I will present our CVPR 2021 paper, Out-of-Distribution Detection using Union of One-Dimensional Subspaces. This is a joint work between the University of Central Florida and University of Toronto. Out-of-distribution detection is concerned with handling novel situations at the test line. For example, assume your classifier is trained to classify handwritten digits. What should it do if it encounters this character at the test line? Ideally, it should be able to flag it as an outlier, something that it was never trained for. But the question is, how can you make your in-distribution samples more distinguishable from outliers without knowing the distribution of the outliers? Because by definition, we do not have any information on the out-of-distribution samples. Motivated by this question, we propose a solution to minimize the error regardless of the distribution of the out-of-distribution samples. Our method does not need access to out-of-distribution samples for hyperparameter tuning and does not need to generate or reconstruct samples. This makes our method easy to apply to existing architectures and different modalities. To understand the intuition behind our method, let's consider this binary classification problem. The red class is a conventional Gaussian distribution, but the green class only has variation along the single direction. It is known that in this case, the classification error will be zero, as the samples drawn from the red distribution lie on the green line with probability zero. This is true independent of the shape of the red distribution, as long as it is a different distribution from the green distribution. To discuss this in more detail, let's define P sub I as the probability that the sample belongs to the green distribution and P sub O as the probability that the sample belongs to the red distribution. Also, let's define delta as the difference between the means and B as this distance metric. It is shown that the classification error probability is upper bounded as this. So regardless of the values for P sub I, P sub O, the mean, and the covariance matrix of the red distribution, we can minimize the error probability by decreasing the determinant of the covariance matrix of the green distribution. In the extreme case, where the distribution is degenerate and the determinant approaches zero, the upper bound also approaches zero. So we propose to make the distribution of the in-distribution samples as compact as possible in the feature space. To do this, we train the feature extractor such that the class membership probability is assigned using absolute value of the cosine similarity between the feature vector and some predefined directions in the feature space. This way, samples from each class will lie on a one-dimensional subspace. So you can also enforce orthogonality on the subspaces to maximize the interclass distance. At the test time, we extract the first single vector corresponding to the feature vectors of each class. This vector represents the class subspace. Then we extract the feature vector corresponding to the test sample and calculate this quantity, which we call a spectral discrepancy. And it is basically the angular distance to the closest subspace. Then we can calculate with what probability this distance is less than a critical distance. If this probability is zero, we flag the sample as out of distribution. We can calculate this probability by collecting Monte Carlo samples from the trained model. To visualize this, these are the feature vectors extracted from a vanilla network, and these are the same feature vectors extracted using our training method. As you can see, the feature vectors are distributed much more compactly. Now this is the same figure after normalizing the feature vectors, since we do not care about the norms and only care about the angular distance, and it shows the compactness even better. At the test time, we can see that the out-of-distribution samples are distributed more uniformly on the unit sphere, and this characteristic can be used to flag them more easily. This figure shows that the proposed spectral discrepancy, which is the angular distance to the closest subspace, can effectively distinguish between the in-distribution samples from CVPR and out-of-distribution samples. Most of the in-distribution samples have a spectral discrepancy of less than 1 degree, while the out-of-distribution samples are spread more uniformly in the feature space. This leads to quantitative improvement comparing to the baseline. Our method is modality independent, and we applied it for human action recognition in videos with minimal change and show that it can improve the OD detection compared to vanilla network. In conclusion, we showed that we can improve the out-of-distribution detection performance by engineering the distribution of the in-distribution samples. Our approach does not have hyperparameters, does not need extra information, and can be easily applied to existing methods with minimal change. Our approach is modality independent and can be applied to different input types. For more information on implementation and more theoretical discussion, please take a look at our paper and our GitHub repos. Thank you.
Hi, this is Mobshad Naim Rizvi. I am going to present exploring complementary strengths of invariant and equivariant representations for few-shot learning. This work has been co-authored by Dr. Salman Khan, Dr. Fahad Shahbaz Khan, and Professor Mubarak Shah. Deep learning methods crucially rely on large label datasets. However, learning from large amounts of label data is often infeasible for a multitude of reasons. For instance, an event can be very rare so that there won't be many samples for that. Besides, manual annotation is costly and also might depend on expert knowledge. Few-shot learning is one of the dominant approaches to address this problem. Few-shot learning methods generally train a model on a set of base classes. From there, the goal is to adapt the model to novel classes with only a few examples. However, this task is very challenging because both the amount of data and annotation are limited. Optimization-based meta-learning is one of the dominant approaches for few-shot learning, where the objective is to obtain a good set of initial weights by applying gradient-based updates. Few-shot learning can also be solved by metric-based meta-learning approaches, where a generalized metric space is learned to cluster novel classes. Recent works have shown that simple transfer learning based methods can achieve state-of-the-art performance on few-shot learning tasks. This set of methods stem from the idea that the quick adaptation in meta-learning based methods crucially depends on feature reuse. The success of simple transfer learning based FSL methods brings in an interesting question. That is, how far FSL can be improved by simply improving the base feature extractor. To answer this question, we investigate inductive biases in CNNs. Inductive biases reflect our prior knowledge regarding a particular problem. State-of-the-art CNNs have different inductive biases in their designs. For instance, translational equivariance, local neighborhood relevance, sparsity. In this work, we focus on two broad classes of inductive biases, invariance and equivariance. Invariance achieves better class discrimination by learning a compact class boundary. However, invariance does not achieve optimal generalization performance. The common examples of invariance in CNNs include invariance to natural perturbations and image transformations. On the other hand, equivariance helps in learning better transferable features, leading to better generalization performance. However, unlike invariance, equivariance is not optimal for class discrimination. The common examples of equivariance in CNN stems from the idea of generalizing translational equivariance. In this work, we aim to leverage the benefits of both invariance and equivariance. We hypothesize that if we combine the complementary strengths of invariance and equivariance, it should lead to better class discrimination and better generalization performance. We enforce invariance and equivariance to a general set of geometric transformations like similarity transformations and affine transformation. We quantize the space of geometric transformations for easier optimization. Finally, we solve this task in a multitask learning framework. We enforce transformation invariance through instance classification. For this, we use a contrastive loss to map together the differently transformed versions of the same image. We find that drawing negative samples from the memory bank improves convergence. The objective function and architecture are provided below. We enforce transformation equivariance through transformation classification. We create proxy labels for different transformations. The transformation classification task enforces the Bayes network to retain transformation equivariant features. The objective function and architecture are provided below. We also incorporate self-distillation to learn better representations. We introduce a novel multi-head distillation objective that ensures the transfer of learned invariant and equivariant representations. The objective function for multi-head knowledge distillation is provided below. Here is our overall network architecture. The neural network f theta is the base feature extractor to which we pass multiple transform versions of the same image. Here, the three heads learn equivariant features, discriminative class boundary, and invariant features respectively. During multi-head self-distillation, we transfer knowledge between all these heads from a teacher network. The overall training objective is given below. We evaluate our method on standard FSL benchmark CIFAR-FS and FC100. We find that even without multi-head self-distillation, our proposed method greatly outperforms previous SOTA FSL method. We see a similar trend in mini-ImageNet dataset. We also achieve SOTA performance on TRD ImageNet dataset and especially on the very challenging metadata. We perform extensive ablation experiments to demonstrate the effectiveness of different parts of our solutions. Please refer to our full paper for explanations about these experiments. Thank you for your time and interest. Our code is available at the following link.
Hi, I'm Liana Georgescu and today I'm going to present our work on anomaly detection in video via self-supervised and multitask learning. This is a joint work with Antonio Bărbolău, Radu Ionescu and Marius Popescu from the University of Bucharest, Fahad Khan from Mohammed bin Zayed University of Artificial Intelligence, and Mubarak Shah from the University of Central Florida. Anomaly detection in video depends on the context. On the left-hand side, we have a truck driving on a highway, which is normal, while on the right-hand side, we have a truck driving through the Christmas market, which is abnormal. Addressing anomaly detection through a single proxy task, such as predicting the future video frame, is suboptimal, since the proxy task is not perfectly aligned with anomaly detection. Therefore, we propose to perform anomaly detection by jointly training a model on multiple proxy tasks to reduce the non-alignment of the model with respect to the anomaly detection task. We introduce the error of time, motion irregularity, and model distillation as proxy tasks for anomaly detection. We pose anomaly detection in video as a multitask learning problem, integrating multiple self-supervised and knowledge distillation tasks into a single model. Performing anomaly detection at the object level increases the localization accuracy of anomalies and decreases the false positive anomalies caused by background changes. Therefore, in our framework, we use an object detector. Then, for each detected object in the frame I, we create an object-centric temporal sequence. Our first proxy task is learning the error of time. We incorporate this task in our framework because during inference we expect the error of time to be harder to predict for objects with anomalous motion. At the bottom we present the forward and the backward object-centric sequence. Assuming that some anomalies can be identified through irregular motion patterns, we train our model to predict if an object-centric sequence has consecutive or intermittent frames. At the bottom we present a regular sequence where the frames are consecutive and an irregular sequence where some frames are skipped. Our model also learns to reconstruct objects detected in the normal training videos via middle bounding box prediction task. The last proxy task is model distillation. During inference, we expect high prediction discrepancies between our model and the YOLO-v3 teacher when we encounter an object with unusual appearance. This is our model composed of a shared 3D CNN and 4 heads, one for each proxy task. First, we detect the objects in video using YOLO-v3. Then, we pass each object-centric temporal sequence through our model to predict the output of the proxy tasks. Our architecture is composed of a shared CNN and 4 independent prediction heads. The shared CNN uses 3D convolutions, while the heads use 2D convolutions and dense layers. When we started to jointly optimizing our model on multiple proxy tasks, we observed the need to increase the width and the depth of our neural network to accommodate for the increased complexity of the multitask learning problem. We therefore employ a set of 4 3D CNNs considering all possible combinations of shallow, deep, narrow, and wide architectures. Our 3D CNN model is trained by jointly optimizing it on the 4 proxy tasks. We empirically observe that LT4 has a higher magnitude than the other loss functions, dominating the joint loss without a regularization term. In our experiments, we fine-tune lambda with respect to the validation results of the joint loss of the proxy tasks. As before, we extract object-centric temporal sequences. Then, we pass each object-centric sequence through our neural model, obtaining the output of our 4 prediction heads. In the end, we compute the final anomaly score of an object as the average of the anomaly scores given by each prediction head. We use 3 datasets in our experiments, namely Avenue, Shanghai Tech, and UCSD PET2, Shanghai Tech being the largest one. These are the state-of-the-art frame-level AUC performance on the Avenue dataset. Our framework applied at the object level obtains a frame-level AUC of 91.9%, surpassing all previous methods. These are the top 2 results. These are the state-of-the-art frame-level AUC scores on the Shanghai dataset. Our late fusion method outperforms all previous works, reaching a new state-of-the-art performance of 90.2%. These are the state-of-the-art frame-level AUC performance on the USCD PET2 dataset. The previous state-of-the-art reports a frame-level AUC of 99.2%, but our method still manages to surpass all previous works, reaching a new state-of-the-art frame-level AUC of 99.8%. We conduct an ablation study to assess the benefit of including each proxy task in our joint multitask framework. We observe increasingly better results as we gradually add more proxy tasks in our joint optimization framework. We also include an experiment at the frame level to emphasize the importance of the object level. We illustrate a set of examples extracted from our runs on the benchmark datasets. It can be observed that we can detect anomalies related to human interactions and vehicles. In conclusion, we have proposed a novel anomaly detection method based on self-supervised and multitask learning. We perform an ablation study showing the benefits of jointly learning multiple proxy tasks for anomaly detection in video, and as a future work, we will consider exploring additional proxy tasks. If you find our work interesting, please check out our paper. Thank you for watching.